This is probably the last time you will see quadratically constrained optimization, both convex and non-convex. We are, again, looking at the non-convex case, which means we don't even need to consider integrality in the variables because the problem is non-convex anyway, and it needs some branching. It needs spatial branching, it needs tight convexification cuts, it needs a tight relaxation. We saw already this morning that if in the non-convex case, you need to define these auxiliary variables because that's the only way to allow for branching. It's the only way to get a valid relaxation, which means it's the only way to ensure that at the end you get a global optimum for your problem. We saw this relaxation this morning. If you have this sort of relaxation with a semi-definite, positive semi-definiteness constraint in a relatively large matrix, one advantage of this is that you only need to define one such matrix Y, even if you have a lot of quadratic constraints, because they are going to be using the Y variables are going to be defined on the same set of variables X. However, you still have a non-convex problem, of which this is just a relaxation. If you want to solve it to global optimality, you will need to do some form of branching, some form of spatial branching. So the branch and bound scheme that you already saw, that you already knew for mixed integer linear programming, and which we extended yesterday to the non-convex nonlinear case, can be applied in this case as well. In every node of the branch and bound tree, you need to get a valid lower bound by solving a semi-definite optimization problem. So this guy here. So this is your relaxation, which you will have to solve at every node. We get a solution which we call X bar and Y bar. If Y bar is equal to X bar times X bar transposed, that means that the constraint that we relaxed before and turned into a semi-definite, positive semi-definiteness constraint is actually satisfied. So the solution you have is feasible for the original problem. You discard the node. Yes? This is K. Sorry. So there are M constraints. All of them are indexed by K. Thank you. So if the equation Y equals X times X transpose is satisfied by the current solution, obviously the node is feasible. You drop it. You get not only a lower bound, but also a feasible solution which you can update, which you can use to update the cutoff. Otherwise, you may need to branch. And branching means that you need to create two new nodes by branching on one of the variables. It can be any variable. Both the X and the Y variables are suitable. And you create two new nodes, each of which will have, as a relaxation, an SDP, a semi-definite optimization problem. At each such node, you have to do this. Now, semi-definite optimization problems are, at the moment, efficient, but not that efficient. So for a few thousand variables, they can give you a solution, but they are clearly not as fast as linear optimization problem. There's the real issue, though, with using an SDP and semi-definite optimization solver at every node is that they don't have warm starting. So as you know, in mixed integer linear optimization, you have to solve a linear optimization problem at every node. You possibly have to resolve it every time you add a cut within every branch and bound node. But resolving a linear optimization problem in a node with the dual simplex method is extremely fast. You need a number of simplex iterations that is very small compared to the size of the problem. This doesn't happen in semi-definite optimization, which means that given that at least all the algorithms I know that solve semi-definite optimization problems are interior point algorithms, that means that they need to start from scratch every time. This is a huge computational burden. Having a mixed integer SDP solver is going to solve a few problems, but not very large. So one idea then would be, okay, let's still keep in mind this semi-definite optimization, positive semi-definiteness constraint. And let's try to understand how we could at least try to approximate it. So let's try to see if there's any way to get a relaxation of this relaxation, which is easier to handle by the current technology. So mixed integer linear optimization solvers. And one idea was by Sherali and Fraticelli in 2002, and it's a relatively easy idea. So again, you don't want to enforce this constraint explicitly because it's non-convex, but you still have the positive semi-definiteness of y minus x times x transposed. So suppose you don't add this constraint, this positive semi-definiteness constraint, but you stick to this initial relaxation without this nonlinear problem, and you solve the relaxation. You will end up with a bound that's relatively bad because you don't even have McCormick. Or you could put in McCormick inequalities and you would get a slightly better bound, but not as good as with the positive semi-definiteness constraint. That should be, yes?
Just a quick question. This relaxation doesn't depend on bounds at all, so you cannot run. Or how do we run?
The relaxation doesn't depend on what?
If there are no integer variables, how do we branch this?
The same way you do in mixed integer nonlinear optimization, right? So this is only a relaxation, much like the McCormick relaxation you would get.
Right, but if I don't have any integer variables, then and if I solve this as a relaxation, I get an infeasible solution to the original one where y is not equal to etc. Then what is the next relaxation on the branch?
You need to branch on a continuous variable.
Yes, but that would still give me the same relaxation, right? How do you define the relaxation?
Yes. I'm not aware of any implementation of this, but you would need to branch on a continuous variable, that's for sure. We could try to figure out what will happen there. So take one variable xi. Xi must be either less or equal than alpha or greater or equal than alpha. Once you impose that constraint, is there any extra bounds that you can enforce on other variables, or is there any linear constraints you can enforce so that it cuts off your current solution? I'm not aware of any algorithm that does it at the moment on a semi-definite optimization relaxation, but you would have to do that. If you think about it, the work by Saxena Bonamili that we saw this morning, it went more or less in that direction, right? Because it was having to do with just a quadratic constraint. But once you branch on any variable, then the quadratic, yes?
And we need some dependence on the bound of the variables to actually, for example, McCormick. Something we need to depend to branch. We need something to depend on bound.
Yeah, that's correct. So you're outside of the semi-definite cone. Or no, you're actually inside the semi-definite cone. Your current solution satisfies, okay? And how can you split the cone? Because you're going to split the cone somewhat in two parts so that you cut off the solution in both sides. I don't have it off the top of my head. We can reason about it later if you want. I mean, even if we found a way, it would still not be a great idea because you still need to solve a semi-definite optimization problem. So the idea here is to forget about the whole cone of positive semi-definite matrices and instead say, well, if the solution I get from the current linear relaxation, in case I decided not to use the SDP, the semi-definite optimization bound, is to check if the semi-definite optimization constraint is satisfied. If it's satisfied, then, well, you need to do this branching. Otherwise, given that this matrix is not positive semidefinite, there must exist a vector A such that this thing is strictly negative. Because positive semidefiniteness of this matrix means for every vector, A transpose matrix times vector is greater or equal than 0. Well, this means that you can, if you find this vector A, all you need to do is use the vector A to create a new cut where A is obviously the coefficient, which you just found, and y times x transpose is a set of variables. This is, again, you're enforcing positive semidefiniteness one linear inequality at a time. How many such inequalities there are for a positive semidefinite cone? A few, right? But this is a linear cut. And if you add this and you repeat, the simplex method, the dual simplex method will take very little to reoptimize it. With some caveats. So we could even come back from this and say, this is just a cut. So separation of this cut is easy. We'll see later what it is. And you don't even need to be in a branch and bound method. So you can apply this as a cutting plane method. So you solve the initial relaxation, you find one such cut, you add it, you resolve it, etc. So you're using we can use a cutting plane algorithm at the first few iterations until, for example, we don't find anything more. Precisely as it happens in mixed integer linear optimization. And once we are done, we can't find any such cut anymore. Then we start the branching, we start the branch and bound process. So tell me what A can be suitable here. Well, it's on the slide, but basically all you need is a minimum eigenvalue, which you can find very easily. Of course, if the eigenvalue is negative, and the minimum eigenvalue has to be negative, because otherwise the matrix will be positive semi-definite. And corresponding to that eigenvalue, we get an eigenvector V, which does exactly what I need from A. That is, it's definitely going to be such that this quadratic form is strictly negative because of the negativity of the eigenvalue. So here's your cut. The cut is simply derived from the eigenvector corresponding to the minimum eigenvalue and from the variables y and x transposed. And this is your, if you want, this is your cutting plane algorithm or your node solution or your node separation routine that finds linear cuts. Does it look nice? I mean, why not? You don't like it? Okay. No, I mean, it looks nice so far because it's all linear cuts. You need a lot of them because the cone of positive semidefinite matrices, it's even hard to approximate with linear cuts second order cones in more than a few variables. And there you require quite a few linear cuts just to get a decent approximation of the second order cone. Imagine with a positive semidefinite cone. There's something even more. There's something even worse here, which is density, or we wish for sparsity, but what we get is a lot of density, because if we get any eigenvector, the eigenvector can be rather dense, which means that the matrix of coefficients of this inner product is going to be V times V transpose, where V is your eigenvector. If V is dense, this is a very dense matrix of constraints, which could be up to O of n square, or if your original problem had n variables, you end up with a problem that has an O of n square variables, and every such cut you produce may have up to n square constraints. That's a nightmare. So forget solving problems with 1,000 variables simply because you're already adding another 1,000,000 variables just to add the auxiliary variables. And then for every cut you add, every cut is going to have 1,000,000 coefficients. That's preposterous. And then every solver will just refuse or go on strike instead of solving the problem. So this problem has been tackled in the past. So one method proposed by by this paper, for instance, finds an eigenvector, because you still need an eigenvector corresponding to a negative eigenvalue. But you can try to sparsify that while trying to maintain the fact that your cut is violated, so you need to make sure that this cut is violated even if you changed the components of V a little bit. And if that is the case, then you manage to make the cut a bit sparser, and the linear optimizer in the branch and bound is going to be grateful. So questions? Is positive semi-definite when y is equal to x times x transpose. Yes, so I don't understand why you want to introduce another variable. How would you model what, sorry? No, you're right, sorry. This was a compact form, and I didn't want to write the Schur complement. But if you put the Schur complement instead of this, then you're gonna. So what you get as a solution is x bar and y bar, and you check the Schur complement 1 x bar transpose and then x bar and y bar. If this is positive semi-definite, then you're good. You probably need to branch. Otherwise, you find the minimum eigenvalue and the corresponding eigenvector of this matrix. Suppose it's V, and this is going to be an n plus 1 dimensional vector. And the cut is going to be like this then. V x, not x bar, x transpose, x, y, v greater or equal than 0. More questions?
That is the linear constraint.
Yes, so note that. I will fix it in the slides, but definitely that is, as you said, it's a quadratic constraints, but although it might be, well, this is actually convex or non-convex, you think? It's wrong. I don't advise using it, but is this a convex constraint? We did it in the morning on a different session, but you can rewrite it as V times V transpose times Y minus V transpose X square greater or equal than 0, which means V transpose X square less or equal than a linear term. So how do you write the other approximation cut for a second order cone constraint and a rotated second order cone? The first part is easy, I think. Are you going to just take the gradient of that stuff? If yes, why? And if not, why not? So who of you converted the first non-rotated cone? And how did you convert? How did you rewrite it if you did? So if you write simply this cone, sum for I from 1 to n minus 1 of xi square minus xn square less or equal than 0, applying other approximation to this is incorrect because that is not a convex function. What you need to do is to translate this into xn greater or equal than 0, and then xn greater or equal than square root of the summation of the sum over I from 1 to n minus 1 of xi squared. This is a convex function, and the other approximation over this constraint is simply xn greater or equal than whatever first degree Taylor series approximation you can have on this square root. So I think the first part is easy. The second part is not so easy. Let's write the solution to the first part. Xn greater or equal than, well, I need to compute g of x star plus gradient of g computed at x star times x minus x star, which is simply equal to, in our case, the sum over the square root of the sum over I from 1 to n minus 1 of xi squared plus the gradient is going to be, it's going to have a common term, which is dividing by this, twice the square root of the same thing. So sum over I from 1 to n minus 1 of xi squared. And obviously, this is a star, and there's a star here as well. And then there's going to be a sum here because this is a gradient already. And you have 2 times the summation over y from 1 to n minus 1 of xi star multiplied by xi minus xi star. I think. So xn greater or equal than this is your outer approximation cut for the simple second order cone. That was a simple exercise in outer approximation. Tell me how you do now the rotated second order cone. If you take the square root of both sides, now you end up with something that is not xn on the right-hand side. So let's take the square root. What you have is the square root of the sum over I from 1 to n minus 2 of xi squared less than or equal to square root of 2xn minus 1 xn. This is a difference. So if you just move the square root on this side, now you get the difference of 2 square roots. Forget about convexity. How do you do this?
You write xn minus 1 xn difference of x plus 1 whole x plus xn plus xn minus 1 squared minus xn minus xn.
Okay. So you're taking, okay, so you're taking this as xn minus 1 squared. But that would be a second order. Okay. Then what?
I think it should be xn plus xn minus xn.
Oh, xn minus 1 times xn.
So you need xn.
You want to come here?
Might be wrong.
Yeah, but this is, I mean, this is the purpose of a course, to learn from our mistakes, mine and yours. Sorry, plus.
I think this is equal to that. So now
Without the square root.
without the square.
Okay, so and this is still non-convex, right?
Still not. Yes. This essentially is just in norm.
Mm-hmm. Okay.
I mean, you understand that?
Yeah.
And this we can also, I think, write as a norm.
The other side.
Yeah.
Be careful though. So this is a norm, but it's squared. I think you implicitly remove both square roots. Yes, so this is a square L2 norm. You take this negative square, you can put it on the other side, and now you have a classic second order cone, and you can simply say that now you can take the square root. Yeah, so you take the square root of that, and then you can write a. Right. Exactly. Do you agree? Do you have a better way? But I think this is correct. Oh, wow. You have alternatives? I have one alternative. So this is a norm, so it's convex. This is the product of two, it's a monomial where the sum over all the exponents is equal to 1, which means this term is definitely not convex, but it's concave. So exactly the opposite happens to concave functions when you write concave function greater or equal to something. So what you could have done is say, let's introduce a fake variable t and say square root of 2xn minus 1xn greater or equal than t, and then t greater or equal than square root of the sum over all I from 1 to n minus 2 of xi squared. You get another approximation from this cut by simply taking the first degree Taylor series approximation of this norm function. So, and this is simply because for a constraint of this form, where g of x is convex, then you get the other approximation cut, which is, let me repeat it here, but I might have written it already there. But gradient of g computed in x star times x minus x star less or equal than 0. This is a valid cut for a convex function g. So if g is convex. If h is concave, if g is convex, this constraint is a convex constraint. If h is concave, then h of x greater or equal than 0 is a, I wish you said a concave set, because that obviously doesn't exist. Yes, this gives you a convex constraint, which is satisfied by a convex set of points. And you can do exactly the same thing and say h of x star plus the gradient of h computed at x star times x minus x star greater than or equal than 0. Much in the same way, or you can rewrite it just by flipping the sign to h, which gives you a convex function, so everything else comes naturally. And once you wrote the other approximation for this and the other approximation for that, both will have t in the first degree. You just eliminate them. You just eliminate the 2t, and you get another approximation for a second order cone, a rotated second order cone.